All right, you can start by taking a few minutes, see if you can solve this electric circuit problem. You have two capacitors in parallel. One has capacitance C1, the other capacitance C2. We apply here a voltage V0 constant at time 0. We start off with 0 charge in both of them. So I'll give you that Q1 0 is 0 and Q2 0 is 0. And the question is, we want to find out how these two capacitors charge up. Yes?
We'll need to do two separate voltage drop equations, right?
Yes. The question is, will I get two separate voltage drop equations? Yes, because there are two independent closed circuits here. There's actually three closed circuits. One is ABGH, another is BDFG, and another is ABDFGH. But there's only two independent pieces of information. All right, at least you've had a start in thinking about it. And we're going to do this problem now, with your help, of course. But first, I would like to address a question that has been asked to me several times about the evaporation of a spherical drop. Okay, it's question 3 on the graded homework for tomorrow. And the idea is this. You have this drop, and we're going to assume it stays spherical, like a drop of water or a drop of something which is going to evaporate into the surroundings. Okay? So you have very dry air surrounding this little water droplet. So the vapor pressure in the air is so low that essentially all the water molecules are going to evaporate from the surface of this droplet. So it's not an unreasonable assumption that the rate of change of the total volume, and the volume of a sphere is 4/3 pi r cubed, the rate of change of that is proportional to the surface area. And the surface area, of course, is 4 pi r squared. I mean, that's a very reasonable assumption. So let us write this down in a mathematical framework. And it says that the d by dt, the rate of change of the volume, which is 4 pi over 3r cubed, is proportional to 4 pi r squared. But you know it's decreasing, so it's a minus constant times 4 pi r squared. Now you're not told the constant. If I differentiate this, I get 4 pi r squared dr by dt on the left-hand side. So I get 4 pi r squared dr by dt equals minus k 4 pi r squareds. The 4 pi r squareds cancel, and so I get a lovely, simple differential equation. Dr by dt is minus k, which I know about 90% of you can solve. Now, when you solve it, you'll have a free constant. So you have two unknowns, that free constant and the rate of evaporation k. But now I give you two bits of information. I told you what the starting size was of the droplet. The radius initially was something like 2 centimeters, which is a hell of a big droplet, actually. I should have been talking millimeters. But anyway, we're using centimeters, and minutes was our unit of time. So we solve this equation. We have two unknowns in it, k and c, but I've given you two bits of information, and from those bits of information you can get both the constant and the k. So, not too hard. Good. Good. So that takes care of that one. Yes, question? Yes, it would. You'd find the k turned out to be minus something that you would, if you'd have taken it to be a minus k, you'll get k equals a plus something, and if you wrote it as k, yes. Good. Did you do it that way? Yeah? Good. Excellent. Very good. Let me draw your attention to one. I'm failing all these tests. The quiz, I actually put down the wrong asymptotic value of where the Q of t goes to, but this is going to be changed. This will be changed. In the answer sheet, I put down it went to 1 rather than, it starts at 1, but it ends up, of course, at the 3/2. Good. Now, onto the electric circuits. We want to charge up two capacitors at the same time. And so we link up the circuit this way. Actually, as you can see, we could do any number. We could put lots of them. Could have another one over here and so on. Okay? We're going to use this old battery here to charge them up. And we have a resistance in the circuit, R. Right. Kirchhoff 1 says what? At the junction B, where the current splits, the current going into B is I. The current coming out is I1 and I2. And we know that the current into a junction and the current out of a junction have to be the same. So that's one piece of information. We know also that the currents are related to the rate of change of the charges on the two capacitors. They're just the derivatives with respect to time. So now I go to my second Kirchhoff law. I'm told that around every closed circuit, the total voltage drop is 0. That's equivalent to saying if I go around this way and I go around this way, I get the same voltage drop. So, let's choose the circuit A, B, G, H. Around A, G, B, G, H, when I close the switch is now closed at T0, T equals 0. I'm going to have VA minus VB plus VB minus VG plus VG minus VH plus VH minus VA equals 0. Now let's express these things. VA minus VB, there's a strong resistance R in that element, in that bit of the line, and the current running through is I. So this will be R times I. The current, the voltage drop across BG is what? 1 over C1, Q1. The voltage drop across GH is 0. Now, a young lady asked me last time, she was a bit puzzled, and she was right to be. She sort of said, well, isn't there a bit of resistance along here too? Of course, that's true. Along every bit of the wire, there's a resistance. So, strictly speaking, if supposing I had little r as the resistance in ohms per unit length of the wires I was using, I would have to add that in. Like on the top circuit, I'd have to add in little r times the length of AB, and so forth and so on. So I'd get a little bit of extra terms with little r times the length. In other words, the resistance due to the wire itself. But I'm going to assume that the actual applied resistance we put in the circuit is much bigger than the actual resistance along the wires. Okay? Okay, or we can think of, alternatively, we can think of the resistance along the lengths of wire are all kind of, we condense it. We pretend that all of it is located in the one stretch up here. Okay, so we won't worry ever about the little bit of resistance along the particular wires themselves. Right, so this is equation number 1, and we have a final term because VH minus VA, we're given that VA minus VH is V naught, so this is minus V naught equals 0. What's the next circuit? What's the next circuit you'd like to choose? Okay, BDFG. BDFG. Okay. Now, what is the drop across BD? Assuming 0. So it's 0. The drop across DF. Yeah. The drop across FG. And the drop across this one. Remember, the current is coming this way. Right. Minus 1 over C1 Q1. Okay. So now I have all the information. If I go to the circuit ABD, FGH, I would only get the sum of those two equations. Yes?
I'm sorry, why is it minus V naught or minus Q1 over C1?
Okay. It's minus V naught because it's VH minus VA. But you're told that the voltage drop VA minus VH is plus V naught. Right. Likewise, here, the current is running this way, so the charges will be pluses and minuses like that. So the voltage drop going this way would be the negative. All right. So this guy from here we know the information that Q, this is true for all time. So differentiating it, I get 1 over C2 I2 equals 1 over C1 I1. By differentiating this equation here, we'll call this, this is 1, this is 2, and this is 3. By differentiating 3. So now I have a relation between I1 and I2. Yes, question. Yes, and this is true for all time. So I differentiate it with respect to time. So I get 1 over C2 dQ2 by dt equals 1 over C1 dQ1 by dt. Okay? And that's this. So now I know that I2 is I1 times C2 over C1. Then from equation 1, we have I equals I1 times 1 plus C2 over C1. Because I2 is C2 over C1, I1. So now I have a relation between I and I1. Okay. Now I'll go to equation 2. From equation 2, I have R times I, but I is I1, so this would be R times 1 plus C2 over C1, I1. But what is I1 in terms of Q, or Q1? It's dQ1 by dt. So this is just the term R times I. Because R times I is R times I1 times 1 plus C2 over C1, but I1 is dQ1 by dt. Plus 1 over C1 Q1 equals V naught. So I can write this as dQ1 by dt plus 1 dividing across by this. I get this is R times C1 plus C2 times Q1 equals V0 over R 1 over 1 plus C2 over C1. So now I have an equation for Q1, a first order differential equation for Q1, which I can solve. I know the initial condition. The initial condition I gave you was Q1, the initial charge was 0. So voila. How do you solve this? Well, these are all constants. This is a constant, so you can use the separable method, or you can use the fact that the equation is linear and get an integrating factor. I'll just write down the answers for you. The answers are that Q1 of t will be, actually, can anybody guess what the answer will be? What do you think the long time answer will be? How much charge will be on this capacitor after we wait a sufficiently long time? We'll see roughly how long that is in a minute from the answer. Who said that? Good man. C1 times V naught. That'll be because the capacity of the thing is C1. Essentially, when the charge, when you go for a long time, the current stops running, the current goes to zero. So effectively, there'll be no current running in anything. This will be charged up, this will be charged up, and essentially the voltage drop then across here has to be the voltage drop across there. So this would just say that Q1 over C1 is V naught. So in fact, that's correct. So it's Q1 is C1 V0, 1 minus e to the minus t times R times C1 plus C2. And Q2 of t, what do you think Q2 of t is going to be? Right, C2 V0. 1 minus e to the minus t, C1 plus C2. So what's long and short in time? Well, essentially this term initially, of course, is 1 when t is 0. But when t gets quite big with respect to r times the sum of the two capacitances, then this term here will be negligible with respect to the 1, and you will be asymptoting to the final charge that's sitting on that capacitor. So, yes, question?
How did you get the equation here at the bottom from 1?
This one. This one.
Yeah.
Okay. I is equal to I1 plus I2. But I know I2 is C2 over C1 I1. So therefore, I is equal to I1 times 1 plus C2 over C1. And that's here. Okay. So, really, linear circuits are very straightforward, aren't they? So you can make up circuits to do interesting things yourselves now. What do you think I'd have gotten if I'd put another capacitor here with capacitance C3? It would charge up, yeah, to C3V0 and so on. But I'll take longer, because probably then the time you'd find you might like to try it out, see what the time scale, do you think it might be C1 plus C2 plus C3? Okay, when we were charging up one capacitor, it was just C1V0, 1 minus e to the minus t over R C1. Now, two in parallel, okay, this C becomes the C1 plus C2. So the time taken to charge up the circuit, in other words, the time for this to become negligible, is a little longer because you have the second capacitor in there. The system has had to work a little harder, right? Yes, question?
So how will this change if the capacitors were in series?
Why don't you work that one out? Yes, yes. Good question. The question is, supposing you put the capacitors in series. In other words, I put them in the same circuit. All right? It's all yours. I'll be asking you next day. But that's a good question. Very good. Any questions on this? Any questions on the ideas? Essentially, we have the relation between current and rate of change of charge. We have Kirchhoff 1 and all the possible independent closed circuits for Kirchhoff 2. Yes, question?
When you ask how long is very long,
Yeah.
are you going to solve for that, or is it just like 2 times 2?
No, I would ask you maybe, roughly, when does it, for instance, I might say, how long does it take for Q1 to get to half its final charge? Then what would that be? So supposing we ask that question. Say, let's call it T1.5 is the time for Q1 at T1.5 to be half of its final value. Okay? Now, this guy, of course, is equal to, from the answer, it's equal to C1 V0, 1 minus e to the minus T1, I put the T1.5, divided by r times C1 plus C2. And that's equal to a half C1 V0. So, this would say that 1 minus e to the minus T1, with a half on it, r times C1 plus C2, is equal to a half. Or it says this guy is equal to a half, which means that the T1, a half, would be r times C1 plus C2 log 2. Right, so that gives you an idea of approximately, and if you're working in practice, somebody says, your boss says to you, well, how long will we have to run this thing to charge these batteries up? Well, this is how you'll calculate that. You know, you want to turn the switch on for half an hour, it may be all automated, and you may have to set the original times at which you're going to allow the charging to take place. You want to know, be able to calculate roughly beforehand how long it's going to take. And you can see, because you're doing slightly more work here, you're going to take a little bit longer than if you just won. Good. So linear circuits. Who's the electrical engineer in the audience? Who's one? And there's another. Yeah. You're doing. Now, are you taking linear circuits there yet?
Not yet.
Not yet. Next semester. But you know it all now, huh? Huh? You're an expert, right? Good. Any questions? All right. The next topic, the next application in this set of applications of first order ODEs are going to be bodies falling under the influence bodies falling under the influence reminds me of Saturday nights. So bodies falling under the influence of gravity and friction. Yeah. Now, I have to tell you a little bit about how friction works. In all cases, we're going to imagine we have a sphere. This is a sphere of radius A. And we'll say it's falling. So it's moving downwards. Okay. Alternatively, you can think that we've kept this fixed and the air or the liquid around it is moving up. But we'll think of it falling down with a speed u. So the fluid or the air will flow around it, something like this. Sort of. And that's what we have to kind of figure out. What is the force, the friction force, on a sphere that's falling in some fluid, like water, honey, air, etc. And there are really two regimes. Slow flow and in slow flow the friction force, friction, will be proportional to the velocity. Now, slow flow means very slow. But you may say, look, U equals 3 foot per second. Is that slow or fast? Well, I have to tell you with respect to what. So slow means that the falling velocity is small compared to some other velocity dimension. And we're going to learn what that is. Fast flow, and I have to tell you what that is. The friction force is proportional to U squared, but it's also, we have to remember, friction, friction acts in opposition. Okay? So as this guy is falling down, the friction force is up. If I was throwing this up in the air, the friction force would be down. So we have to be a little bit careful in attaching signs to these things. But we'll see in a moment what the relevant signs are. Now, what's the slow and the fast? The last day of class, I'm going to write on this board. Now, this isn't going to be on your test, so you can sit back and enjoy this bit of the lecture, okay? This is, I'm going to just tell you about how I didn't say you can go home. Now, books figure out empirically, because there is no exact law. I cannot use the equations of fluid mechanics to exactly write down a simple law of friction on a falling sphere, because it depends on different regimes corresponding to slow and fast, and even then there's sort of transitions. So what we'll see is that in one region of whatever parameter space I'm going to be talking about, U like, the friction force will be proportional to U. If, on the other hand, you go a little faster, it's proportional to U squared. I'll draw you the graph in a minute. But the most important parameter is called the Reynolds number, sometimes written with a big R, sometimes written with an R with an E next to it like that. And it's defined as U times some particular size of the ball, which would be A in this case, divided by kinematic viscosity. That's a measure of the stickiness of the fluid. Okay? It's a measure of the stickiness of the fluid. Example, for air. For air, the kinematic viscosity, what are the dimensions? I'm telling you this Reynolds number is a dimensionless number. It has no dimensions. What is the dimension, therefore, of the kinematic viscosity? This is velocity, this is distance. Sorry? Who? Yes?
Well, I said meters squared per second.
Meters squared per second, absolutely. Yeah. This is meters per second times meter, so it's meters squared per second. Just to be perverse, I'm going to give you a foot squared per second. So this is about 1.6 foot squared per second. Let's work out what the Reynolds number is. This is in times 10 to the minus 4. Big. Let's work out if I'm firing a baseball. Baseball, what? Is a radius of about 1/4 of a foot. Actually a little less, but we'll say 1/4. More like 1/6, isn't it? Yeah. For the radius. So, anybody here a pitcher? I mean, yes, you are. Okay. What is the speed of your fastball?
83 miles an hour.
83 miles an hour. Fantastic. That's very good. With the wind? Yeah. Any softball players here? Among the ladies, maybe? Yes? I saw a hand sort of limply go up in the back. Yes? Are you a softball pitcher? No. Okay. Actually, they fire it pretty fast. They get a good whip. All right. What's your first name? Eric. Eric is 83. I'm going to say that's 88. No, 83. 83, what? It's miles an hour, right? All right, 83 mph. Now I've got to go to foot per second now. So I multiply by 88 over 60, right? So that's equal to, it's roughly 3/2. That 88 over 60 is 3/2. So what's 3/2 of that? That's about 120. So say 120, roughly, feet per second. Okay. So now the Reynolds number for Eric's fastball is 120 times 1/6 of a foot. And now that's foot squared per second, divided by 1.6 times 10 to the minus 4. So that would be 6 into that is 20. 16 into 20 is roughly 1 1/4 times 10. So that's 1.25 by 10 to the 5. Question. Okay, U is the speed at which the sphere is going through the air. Speed relative to the air. A is the radius of the baseball, the sphere. And nu is the kinematic viscosity. Question.
So you just have to use radius for a problem like this, and not to use surface area?
You could use the diameter as well. It's up to you what convention you decide to use. Question.
Is it always going to be a sphere that's falling?
No. I mean, if you jump out of an airplane, you're not a sphere, right? But the difference isn't very different between a sphere, and I'll mention this in a minute. The actual friction force on you and a sphere roughly of your dimensions wouldn't be that much different. Okay? Question.
I just want to let you know you're only 1.7 feet per second off on your estimate.
1 point what?
You're 1.7 feet per second off on your estimate.
Well, thank you. Yeah. All right. I'm glad I have the expert now in the class. I'm going to go to you now for the precise answer in every. All right. Now, engineers plot the following. Engineers plot a thing called drag coefficient. And the drag coefficient, they actually have to plot it for different shapes, like this young lady brought up. But roughly, so the drag coefficient is the force, as the friction force, made dimensionless by dividing by a half the density times u squared. This is roughly a measure of pressure. A pressure. For instance, what keeps an aeroplane up? You have a kind of an aeroplane wing like this. The air goes faster over the top than over the bottom. And so the pressure is higher here than here. And it's roughly by half rho times the square of the velocity. If it was super fast up here and super slow down here, it would be half rho u squared, where u is the speed on the top. So this, and now to make this into a force, this is just a pressure. Pressure is force per unit area. I have to multiply by an area, which we'll say is pi a squared. Okay, that's a cross-sectional area. For instance, it's the area you would see if this sphere is falling on you. That's the circular area you would see going to hit your head. Okay, so this guy is a function of this Reynolds number. Okay, and this is what's plotted. If you go to Google or any engineering textbook on fluid flow or any aerodynamic textbook, there'll be graphs plotting this drag coefficient versus the Reynolds number for various shapes. And roughly it looks like this. So this would be like so this is the Reynolds number here. This is the Reynolds number. And this would be, say, 10 to the minus 1. This would be 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6. And roughly it comes down like this. It comes down like falling like 1 over r all the way down to about here. And then it seems to go constant for a while. Then there's a little bulge, and then it suddenly drops like that. So now I'm going to draw it kind of in sort of pieces. This bit here is very much like 1 over r. This is like 1 over the Reynolds number, 1 over RE. This bit is almost constant, almost flat. Okay, almost flat. So on this bit here, if CD goes like 1 over r, if CD, which is the force divided by a half rho u squared pi a squared, if that goes like 1 over r, which is 1 over ua over nu, 1 over r is nu over ua, then you can see that the force, if I multiply across this equation, the force will be, one of the u's will cancel, one of the a's will cancel, and it'll be roughly proportional to rho times nu times a times u times some constant. In fact, you may remember, maybe in your high school textbook, I think it was 6 pi rho nu is sometimes called mu, or eta, the stickiness, and 6 pi times a radius, a, mu times u. So this slow flow occurs for Reynolds numbers which are of the order between 10 to the minus 1, 10, maybe up to 10. 10 to the 0 is 1. So that's what we mean by slow flow, that the Reynolds number is of the order of 1 or less. Okay? Now, for instance, in blood flow, in a minute, in blood flow, the capillaries are so small and the speed of the blood through is so low that the Reynolds number is very small. So basically, the blood flow in capillaries is low Reynolds number. On the other hand, in a cloud, for instance, if you little water droplets being convected around, they're about 25 microns. That's 25 times 10 to the minus 6 meters. They're also low Reynolds number flow. Okay, even though the viscosity of air is still very, very low, but when you put in velocities, our sizes rather, of 25 microns, it makes the Reynolds number very small. On the other hand, Eric's fastball, gee, he's up here. He's in a region where the drag coefficient is constant. The drag coefficient is constant almost over 2 decades. In other words, factor of 100 in the Reynolds number. That's quite remarkable. So let's work out what happens then. For Eric's fastball, CD is F over half rho U squared A squared is constant. Independent, question in a minute. Oh, this is CD. Okay. So it's roughly constant. So this means the force, if I multiply across, the force is proportional to U squared. So Eric's fastball feels a friction force proportional to U squared. In fact, most ball games, like tennis or anything like that, that ball is moving, unless you're playing tennis in treacle, that your Reynolds number is going to be in this range. So therefore, the drag will be proportional to the velocity squared, in that case, not just to the velocity. Now, if you're working around here, well, it's a combination of both. It's more complicated. There aren't simple expressions then. Right. Now, I want to now show you why this is the case. This is quite miraculous. What's miraculous about this, by the way? Can anybody see what's missing in that formula for force? What's missing? What? Sorry? Mass? No, because there is a rho here. That's in there. Yeah, that's. So what is actually missing? What parameter was in here that's not in here? The viscosity, the stickiness. That's incredible. It's incredible. The friction force at these large Reynolds numbers is independent of the friction. Even if the friction goes all the way down to 0, very small. Or if the friction was very small or a little bit less small, the friction force doesn't depend on it over a large range of these Reynolds numbers. That's incredible. This was a great puzzle for scientists for a long time. It's known as D'Alembert's paradox. And the reason for it is as follows. The reason is there goes your fastball, huh? The reason is as follows. If you're in very slow flow, now we'll say the flow is this way, so the thing is moving this way, or the thing is stationary and the flow is moving past it, like this. Then essentially the flow stays attached to the body. And roughly speaking, of course, the flow actually, supposing this body is stationary and I have a fluid flowing by it, the velocity has to be actually 0 here and going up to its final value far away. Okay? But the rate at which it changes up to its finite values happens over a long distance. So the flow around this is relatively smooth. Okay? And so this is where you have the formula, where this formula for the drag or the force, the friction force, would be this guy. But now what happens as you speed things up? As you speed things up, the region over which the transition takes place from 0, namely the speed on the boundary of the fluid on the boundary, to the speed of the fluid out here, gets much smaller. It's called a boundary layer. And like as the fluid flows up over the boundary layer like this, the pressure is higher here, lowest higher again. But essentially, because there's a little bit of friction, there's not enough pressure to get a little blob of fluid from this high pressure to the low pressure and back up to the high pressure again. So what you get is it'll separate. So the flow separates. So like this. And you get little vortices and things like that coming off. So now the drag really is in this area here, you have lower pressure than in the upstream edge here. And so the difference, it's really the difference in the pressure. This is what's called the wake, the upstream to the downstream pressure. That pressure difference is what acts as the friction force. Now it's absolutely dependent on the presence of friction, because it's the presence of friction that causes these separations to occur and to create a wake. So that's why the position at which this separates is about 108 degrees, I think, for a sphere. So it's almost independent of what the friction actually is. So it's just the fact that you get separation, you create a wake, low pressure region here, high pressure region here. That's why you get the drag. Question?
So you said that velocity of friction force is independent of the viscosity of the fluid itself.
Yes.
So if you threw a baseball through honey and you threw a baseball through air.
Yeah. Right. You'd have to work out what the... I think Eric's fastball, even through honey... No, it would be probably low Reynolds number. Yeah, it would be... Yeah, it'll be a low Reynolds number. So the friction force will be proportional to the velocity then. Okay? You can work it out. Get the kinematic viscosity of honey and figure it out. Right. Now, actually, it's very interesting. Here, at suddenly about 10 to the 5, or between 10 to the 5 and 10 to the 6 of the Reynolds number, you get another drop. So what very interesting thing happens here, this is when the flow goes turbulent. The flow is all laminar, more or less. Laminar meaning sort of regular. Maybe it has little vortices and oscillations in it, but it's not very turbulent. But up here, the flow goes turbulent. And what the turbulence does, you sort of think intuitively it would make the friction worse, but it doesn't. It actually helps the separation points to move downstream, so the wake gets less thick. So in fact, the turbulent drag is less than the laminar drag. And aeroplanes have to watch this, because aeroplanes fly often at Reynolds numbers where they're close to this point here. And you don't want an aeroplane suddenly having a drag of this and then suddenly going into a region of drag like that. I mean, that would be a pretty bouncy ride. So what aeroplanes do, they have little trips on the wings that they actually try to make the flow turbulent. so that they're always operating in the turbulent boundary layer region. So on and so forth. Questions?
Isn't that sudden drop off down there on the right of the graph?
That
What happens when you get close to the wake speed of the fluid?
yeah, we're not near, yes, when you're up near Mach 1 speeds, so when the velocity gets close to the speed of sound, then yes, there are corrections which depend upon a thing called the Mach number, which is the ratio of the velocity to the speed of sound. Yes, but I don't think we'll talk about that today. Okay, so, because I know very little about it. So,
Walking back very briefly, when you have the equation for the drag coefficient there,
Yeah.
what is the character to the left of the A?
the character to the left of the A here, this is nu.
In the above,
Here,
yes.
this one,
U and A in the left.
this guy,
To the left. Oh, it's pi?
that's pi. Fancy not recognizing my pies. Yeah. So anyway, now to get back to first order ordinary differential equations. So now we're going to look at two regimes, slow flow and fast flow. In the slow flow regime, our friction force will be proportional to the velocity. In the fast flow regime, meaning higher Reynolds numbers, the friction force will be proportional to the velocity squared. In both cases, they will oppose the motion. So, we'll first look at the slow flow case. So if you jump out of an aeroplane, you are not in the slow flow case, even when the parachute opens. You're in a slightly different regime. I mean, some guys are crazy enough when they dive out vertically and don't pull their chute till, I think they reach a terminal velocity of, about 200 miles an hour or something, and, with the chute, of course, it slows you down considerably, which is very necessary when the ground is approaching. So, slow flow case. So here's our situation. I'm going to call y positive up. So y is the position of the ball or the mass. V is its velocity. V of t is dy by dt. So, I have a little mass here. Gravity will act down. So the mass is m. Gravity acts down. So the equation, Newton's second law, if the mass stays constant, will be m dv by dt is minus mg, a constant gravity force, minus kv. This is our friction force, and we're saying we're in a Reynolds number range where the friction force is proportional just to the velocity. And we're given some initial condition. V at 0 is some V0. And the question is, find V for all time and find the position y of t for all time. So, this is a very easy equation to solve because it's linear, they're all constant coefficients, it's all the nice things. So I'll rewrite it by dividing across by m, dv by dt, plus k over m, v, let's brought that term to this side, equals minus g. So now I want to solve this. How many of you are taking courses on fluid mechanics right now? Yes. What have you? What sort of things do you study?
They're studying like the force of a fluid on like a surface right now.
Yeah, yeah. The pressures. And, yeah. Mm-hmm. Any deep sea divers here? Any? You do everything, don't you? Yeah. No? Yeah. Because I was just going to ask you, what depth do you have to go so that you feel the same pressure as you feel when you're on the surface? How far down do you go to have to say double the atmospheric pressure? Yeah, about that. About 10 meters, I think. Yeah. All right. So now let's solve this. Integrating factor. Integrating factor is e to the k over mt. Multiply across by the integrating factor times dy by dt, or dv by dt rather, dv by dt, plus k over m, e to the k over mt, times v equals minus g times e to the k over mt. Recognize the left-hand side now is this perfect time derivative. It's the d by dt of v times e to the k over mt equals minus g times e to the k over mt. Integrate. V times e to the k over mt equals, now when I integrate e to the k over mt, I get e to the k over mt over k over m, which is minus mg over k, times e to the k over mt, plus a constant. At t equals 0, I'm given v is v0. This implies that v0 equals minus mg over k plus c. So c is v0 plus mg over k. Right. So, v of t then, dividing across by e to the k over mt, is going to be equal to minus mg over k. So that's the first term, and then plus v0 plus mg over k times e to the minus k over mt. So now let's draw a graph of what happens to velocity. So here's the velocity, v of t versus time. Okay, do you want to throw the ball up first or down? Will I take the v0 positive or negative? Positive. Okay, we threw it up in the air first. So we started here, v0. Where do I end up? After a long time, where do I end up? At minus g mg over k. So I go like this, where this is minus mg over k. In other words, I'm falling down with a final, or what we call terminal velocity, of mg over k. Now, the gal who, yes, how long, roughly, does it take to get there, to terminal velocity? In other words, roughly, how big does t have to be?
Put me on the spot, so my range is perfect.
Sorry?
If you put me on the spot, so my range is perfect.
Oh, you're brave. But what we want is this to be small, to be large, right? We want k over m, t, when that's much greater than 1, that's a symbol for much greater than 1, then this guy will be almost 0, and I'll have reached terminal velocity. So roughly, the time scale to sort of get halfway there is roughly m over k. Now that has the units of seconds, because this has the units of mass per second. So you approach this terminal velocity steadily. Supposing I had thrown it down faster than the terminal velocity. So supposing I start down here, what would happen then? So supposing the V naught is very negative. So V naught now is less than minus mg over k. So it's down here. What do you think will happen? It'll slow down to the terminal velocity. So it will go like that. So it'll go like that. In either case, you'll end up at the terminal velocity. Okay. How about if we wanted the position? We have dy by dt is equal to minus mg over k plus v naught plus mg over k e to the minus k over mt. And I tell you that y of 0 is y0. Now this I'm going to ask you to do, and this is where we're going to start next day's lecture. And I want you to draw the graph of the y. So we start, say, here, we'll start maybe at 0, or 0 position. Now I know I'm going to end up somewhere falling at a speed, so there'll be a minus mg over kt in my answer. So this is y of t versus t. Okay? And I would like you to explain me what you seem to get. So I'd like you to draw what y of t versus t looks like approximately. Tomorrow, 7:15, Math 501. Don't go yet. Now, it's not time yet. The next day, Thursday, 8 o'clock, Math 501. Make sure you go to your recitation tomorrow. Make sure you hand in your graded homework and do well in the quiz. And start the trial exam.